Hi all, in this tutorial we are going to have a discussion on symbol code generator and peephole optimization. So in order to design a good code generator, we should know or we should be familiar with a target machine and also the instruction set available in the target machine. So we are assuming that our target computer is a byte addressable machine which represent a word with 4 bytes and has n general purpose registers R0, R1, etc. to n minus 1, and it also has two address instructions of the form opcode, source and destination, and the following opcodes are available: move, which moves a operand from source to destination; add, which adds a value from an source and destination; and subtraction, subtract the value between source and destination. So we are assuming these conditions. One is it is byte addressable, then these are the registers available, two address instructions are there, and these are the opcodes. Now we know that this registers will not be able to hold whole memory address, so we will be storing the information by certain bit patterns. Okay, so that is referred to as our addressing modes, right? So the source and destination of an instructions are specified by combining register and memory location with addressing mode. Now these are the addressing modes that we have in the target machine. One, absolute addressing mode, in which the value will be available in an address, and this is a form, and the cost of that instruction will be 1. And register mode, the value is available in the register and there is no cost for accessing it. In the case of indexed mode, it's represented by C of R, which means this R will contain some address. We have to add a particular value to that address to get the content, and it is cost is 1. An indirect register, in that case register does not contain value, it will be having address. From that address we have to get the value. Then indirect indexed means there will it's a combination of both this indirect and index. So first we will calculate index mode, then indirect addressing is used. So C plus contents of R will be calculated, that content of that location is taken. So in that case our cost is 1. So when we go through that, you can see that whenever there is a register directly taking from register, whenever the value is directly taken from the register, the cost is 0, and whenever we have to access the memory location, the cost is 1. So these are the example. Move R0, M. So in that case, the content of register R0 is moved to memory location M. Now move 4 of R0, M. So this is the index mode. So contents of R0 plus 4 is taken. Then from that address, a value is moved to M. Then move star for R0. This is index versus indirect addressing mode. So here it is using indirect as well as index. So first content of R0 plus 4 is taken, its content is taken, then again indirect addressing, the content of that memory location is taken. Then one more mode is literal mode, in which the value is directly given and there also added cost is taken as 1. For example, move #1, R0, you have to load the constant 1 into the register R0. So these are the addressing modes that's available in our target machine example. Now, how can we calculate the instruction cost? So we have seen in the previous tables, that is, if there is a register, if the value is available in register, we don't have any cost, and if we have to refer to a memory location, we have a cost of 1. So when we calculate the instruction cost, we will add 1 to that cost. So the cost of an instruction is 1 plus the cost associated with source and destination addressing modes indicated by add cost in the previous table. So this cost corresponds to the length of the instruction. And address modes involving register have cost 0, while with the memory location or letter in them have cost 1, because such operands have to be stored with the instruction. Now, we should minimize the length of instructions, right? So the instruction move R0, R1, it copies the contents of register R0 into register R1, and this has a cost of 1, right? Since it occupies only one word of memory. Now move R5, M. Since there is M, there is already cost of 1, so we have to add one more, so the total instruction cost becomes 2. Now add #1, R3. Already, since it is a literal value, we have cost 1 plus 1. It will lead to instruction cost of 2. Now instruction sub for R0, star or R. See, here there is index as well as indirect addressing mode, right? Here it is index address mode. So subtraction performs source my destination minus source. So destination value here minus source value, right? Now since these are both registers, now the cost of this instruction is 3, right? Constants 4 and 12 are stored in the next two rounds following the instructions. Now some examples are here: move b, r0, add c, r0, move r0, a. Here, since we have to refer to memory location in each instruction have a cost of 2, hence the total cost is 6. Now here move b, a and add c, a. Here two memory references are there, so here instruction cost is 2 plus 1 becomes 3. Here also 2 plus 1 3, hence total cost becomes 6. Now here move star r1, star r0. Since a register have 0, it is 1. Here also two registers is 0 plus 1 1. Since total cost is 2. Now add r2, r1 and move r1, a. Now his total cost is 3. Since this is 1 and here it is 2. Now a simple code generator. So in order to design a code generator, we should understand the target machine. So in the previous slides, we discussed on the target machine that we are assuming. So next, code generation is based on that target machine. The code generation strategy is a generation of target code for a sequence of 3 address statements. And we assume that computer result is in registers as long as possible. Okay, we assume that the computer result is in registers. Okay, we will store that to other location only if their register is needed for another computation or just before a procedure called jump or label statement. Rather than these two conditions, we won't move the value from that register. Okay, so value will be moved to another location rather than the stored register only if that register is needed for another computation or just before a procedure called jump or label statement. Now for a 3 address statement equal to b plus c, we'll generate the instructions add rj, ri with cost 1. Okay, leaving the result in the a in the register r. So what will we do? A equal to b plus c, we will generate add rj, ri. Okay, with cost 1. Leaving the register A in register RA. So this is possible if we have what A equal to B plus C, right? So this is possible only if RA contains B and RJ contains C. Okay, and the B plus C is stored in RA, which is equal to A. So this B will be replaced by the result C plus B. So this is possible only if B is not used for after the statement. So if RA contain B but C in a memory location, we should use another set of instructions. That is, if add C, RA, in that case, if here is a memory location, the cost becomes 2. or move C comma Rj and Rj comma Ra. Here the cost becomes 3 because here cost is 2 and here cost is 1. Now register and address descriptors. This is a very important concept. So the code generation algorithm uses descriptors to keep track of register content and addresses for names. Okay, descriptors to keep track of register contents as well as the addresses for our variables. So a register descriptor keep track of what is currently in each register. Okay, the value stored in each register is kept track by a register descriptor, and whenever we want a new register we will consult this register descriptor. Then an address descriptor, it keeps track of the location where the current value of a name can be found at runtime. Okay, so at runtime when I want the value of a particular variable where that value is stored, that address is given by this address descriptor, and it can be either a register or a stack location or a memory address, and this information can be stored in the symbol table and is used to determine accessing method for a name. Now we'll see a code generation algorithm. It takes input as a sequence of three address statements constituting a basic block. We had discussed what are basic blocks, and statement of the form x equal to y operates z performs the following action. So whenever we have a three address code of the form x equal to y of z, the following sequence are executed. 1. We must first invoke a function getRegister to determine the location L where the result of computation y operand z should be stored. Okay, so after this computation of the result, where we should store the value of this, that location that we have to identify. So in order to get the location, we will invoke a function getRegister. Then second step is consult the address descriptor for y to determine y dash. Okay, the current location of y. Okay, so where is the current location of y? Okay, from which address I can get the value of y? That is determined by consulting the address descriptor. Prefer the register for y dash if the value of y is currently both in memory and in a register. So if the value of y is available in a register and in a memory location, we should prefer the register. Okay, and if the value of y is not already in L, generate the instruction move y dash comma L to place a copy of y in L. Why? In the previous slide we saw that if the register content is already that value, we can just perform a single operation for addition. So that is why we want to move that particular value to that register the location capital L, so that after addition or after performing that operation the result will be in L. Generate the instruction operate z dash where L comma L where z dash is the current location of z. So then next we are performing the operation L operand z dash. Okay, so and prefer a register to memory location if z is in both. Update the address descriptor of x to indicate that x is in location L. Then we have to update the value. So what we have done, we have found a location L where we will keep the result. Then the value of y was copied to L. Then we performed L operand operand no opcode Z. So we as a result we perform y operand Z and the result was stored in L. So then we have to point the x to that L, right? That is why we have written here update the address descriptor of x to indicate that x is in L. Okay. Now, if x is an L, update a descriptor and remove x from all other descriptors so that we can use x for other operations. Now, if the current value of y or z have no next uses, we have to and not leave on exit from the block, and are in register, alter the register descriptor to indicate that after execution of x equal to y of z, this register will no longer contain y or c, so that it can be reused in further instructions. Next is the function getRegisterM. Now the function getRegister returns the location L to hold the value of x for the assignment x equal to y of c. So first is if the name y is in a register that holds the value of no other names and y is not leaf and has no next use after x equal to y of z, then we have to return register of y for L. Okay. Now if we don't have to use it, okay, then we have to return register of y for L and update the address descriptor of y to indicate that y is no longer in L. Now failing one, if we do not do this, return an empty register for L if there is one. Now failing two, if we are not doing this, if x has an x use in the block or op is an operator such as indexing that requires a register, find an occupied register R. Store the value of R into a memory location. If it is not already in proper memory location, update the address descriptor for M and return R. So this statement occurs when we do not have any free register. If R hold the value of several variables, a move instruction must be generated for each variable that need to be stored. And a suitable occupied register might be one whose datum is referenced furthest in the future or one whose value is also in memory. And we leave the exact choice unspecified since there is no one proven best way to make the selection. Now, if X is not used in the block or no suitable occupied register can be found, select the memory location of X as the L. Now, generating code for assignment statement, we have an example D equal to A minus B plus A minus C plus A minus C. So, I can write the three address code as T equal to A minus B, U equal to A minus C, V equal to T plus U, D equal to V plus U with D alive at the end. Okay, and the table you can see a statement T equal to A minus B with code corresponding code generated are move A comma R0 sub B comma R0. Our register descriptor R0 contains T and address descriptor T in R0. Then U equal to A minus C, move A comma R1 sub C comma R0, R1. So R0 contains T, R1 contains U and address descriptor T in R0, U in R1. Thus you can see detail of V equal to T plus U and D equal to V plus U. Now, for other type of statement A equal to B of Y, that is of a particular index of B array I am assigning to A, code generator is move B of array comma R and cost is 2. Now A of A equal to B, move B comma A of array and cost is 3. Now in the case of A equal to star P, move star RP comma A, cost is 2, and star P equal to A, move A comma star RP and cost is 2. Now, if x less than y, go to z, compare x comma y, and if that condition is less than c, jump to z if condition code is negative. Now, x equal to y plus 6, a z, if x less than 0, go to c. So, move y comma 0, add z comma 0, move r0 comma x, and cj less than z. Now, next is peephole optimization. So, what is a peephole is it is a small moving window on the target program, or we can improve the performance of this target program by examining short sequence of target instructions called peepholes, and we can replace these instructions either by some shorter or faster sequence. Okay, identify certain instructions, target instructions, and they are called peephole, and we can improve the performance by replacing those instructions by shorter or faster sequence. Now we will see the characteristics of this peephole optimization. First one is redundant instruction elimination. From the name itself, we can understand redundant means repeated, right? So if there are some repeated instructions, we can eliminate it. Okay, repeated in terms of logic. For example, move r0 comma x, that is moving the coordinate of r0 to x. Then second is move x comma r0, is moving the content of x to r0. See, in this r0's content was moved to x, then here x is moved to r0. So we don't have need to have the statement, right? So we can eliminate the second instruction x comma r0. But condition is that this should not be a label. Okay, so but if move x comma r0 is a label statement, then we cannot remove it. So we should be careful when we identify the peepholes. Now second is unreachable code. So when a particular programmer writes a program, some set of instructions become unreachable, that is it will not get executed. So that is known as unreachable code. For example, I have the statement void add 10 index, return x plus 10, and printf value of x is percentage d comma x. See, since I am executing a return statement, when it reaches here, this statement will not get executed anytime. So this printf statement is an unreachable code. Okay, I can remove it. Next is flow of control optimization. See, in this case, I have moved R1, R2 go to L1. So control goes to L1. Then it is saying go to L2, and the very next statement is L2 increment R1. See, I am telling go to L2 and it is directly L2. So is there a use of this additional statement? The label L1 can be removed, right? As after this these much lines of code, you can directly give L2, right? So it can be replaced by this set of statements. This L1 can be completely removed because it is saying just a single statement of go to L2. So instead of giving a label name, then again going to a particular label, I can directly give the label name L2 here. So it is a flow of control optimization. So there are instances in a code where the program control jump back and forth without performing any significant task. This is reduction in strength. This we have already seen. That is, if we have in that previous example, in the last tutorial, what we saw was a multiplication statement. We replace it by subtraction statement, right? So in this example, it is given as x into 2 can be replaced by x left shift of 1. Okay, shifting left by 1, it has the same effect of multiplying by 2. So it's another reduction in strength. Example for reduction in strength. Now next is machine idioms. That is, we have seen that instead of I equal to I plus 1, if I can give increment I, then it can be executed in a single instruction. So making use of the particular idioms of target machine, we can improve the what we can optimize the code. So these are different ways of peephole optimization. Understood this tutorial? Thanks for watching.